In this video, we will talk about algorithms. An algorithm is basically a sequence of instructions used to solve a problem or perform a computation. In maths, algorithms have been known for thousands of years. For instance, we have the famous algorithm from Euclid to find the greatest common divisor. Nowadays, algorithms are everywhere in our digital lives. Any process performing computations on data could be called an algorithm. In this video, we will focus on algorithms solving computer science problems through the resolution of a fun little coding challenge. We will also see how it is possible to use math to prove things about algorithms and to classify them according to their performances. As this video is rather long, feel free not to watch it all at once. Here are the timestamps of the main chapters. You can skip the ones you may be familiar with, such as the Python 101 for instance. Let's begin. Every year before Christmas, there is a coding challenge called the Advent of Code. Each day, instead of eating chocolates, you go on the website and try to complete the puzzle of the day. The puzzles are designed not to be done by hand, that would take too much time. So, you have to program a little piece of code doing all the computations for you, as a computer is often faster to do many repetitive tasks. Each puzzle is divided into two parts. For both parts, the answer is a single number you have to find. The first part is often not that hard, but the second part is a trickier version of the first one. For instance, on day 14, you have balls on a plane with obstacles. For the first part, you have to compute the load of the plane after the plane has been tilted to the north. For the second part, you have to compute the load after the plane has been tilted north, west, south, then east, 1 billion times. Every completed part gives you a gold star, and for each collected star, the website is revealed in colors. Every problem comes with two text files. The first one is a simple dummy input coming with its solution, so you can see an example of what you're supposed to get to test your program. Every person willing to play during the Advent of Code has also a second text file, their own personal input for the problem. The personal inputs are huge. It is impossible to solve the puzzle given a real input by hand alone. The animation you saw before was on the dummy input. Here is how it looks like on my real input. Every real input is personal and, by the website rules, is not to be shared. So, this video will be about solving a puzzle, and you'll have access to all the code I used to solve the problem and to make this video, but you will have to test it on your own personal input. Now we are familiar with the Advent of Code, let's talk about the Day 5 problem. The first problem that required me to pause and ponder was the challenge of the 5th of December. I realized that this day's problem's second part was trickier than the previous days. Finally solving it brought me joy and made me remember what I loved in computer science and in maths: problem solving and that little feeling of having understood something, the beauty of finding a clever way to tackle a problem. In this video, my goal is to make you feel this little something. Let's get started. In your journey, you help the gardener to plant their seeds. You're given a list of seeds, each one has a number. You're also given 7 maps, mapping seeds to a kind of soil to a kind of fertilizer, fertilizer to water, water to light, light to temperature, temperature to humidity, and finally, humidity to location. For each seed, you have, according to these maps, to find its soil, fertilizer, water, light, temperature, humidity, and location. These characteristics are also identified with numbers. The final goal is to find the location with the lowest number. The input data for the problem is a text file, and on the website a dummy input is also provided to help understanding the problem. Here is the dummy input. As you can see, the first line gives all the seed numbers and it is followed by the description of all the maps. Since a map takes a number as an input and gives another number as an output, we can plot it like so, with the inputs on the left and the outputs on the right. Here, the higher the number, the higher it is displayed. Each map is composed of rules, one per line. A rule shifts a range of inputs to a range of outputs. Each rule is defined by three numbers: the destination range start, that we will plot on the right side, the source range start, plotted on the left side, and the range length. On the first map, the seed to soil map, the first rule is 50, 98, 2. So, the destination range start is 50, the source range start is 98, and the range length is 2. Because the length is 2, that means the range concerns only two seed numbers, starting with the source range start, that is 98 and 99. Since the destination range start is 50, the seed numbers 98 and 99 are mapped to soil number 50 and 51 respectively. The second line, 52, 50, 48, means that the 48 seed numbers 50, 51, 52 and so on until 97 are mapped to the 48 soil numbers 52, 53, 54 and so on until 99. Because I found the visuals to be prettier, the rules of these maps won't always be shown with a grid. From now on, they will also look like this. Though, you must keep in mind we are still dealing with discrete numbers. Since all these rules do is to shift numbers, we will call them the shifters. If on a given map no input characteristic number matches its shifters, the output characteristic number is the same as the input. Thus, on the dummy seed to soil map, if we had a seed number of value 99, it would have been mapped to soil number 51 since it matches the first shifter. On the contrary, the seed number 13 is mapped to soil 13 since no shifter matches with it. To solve the problem, we have to find for each seed numbers the next characteristic number through each map until obtaining the location number, and then finding the minimum of all these numbers. Easy, right? Well, for our dummy input, yes. But on the real input problem, you have 20 seeds, and each map has like 30 rules. So, I do not encourage you to do it by hand. We will create a program to do that for us. Let's begin. A good start is to simplify the problem, to understand what the problem is really about and to discard what's useless. Each map is what we call in math a function. A function is an object taking one or more inputs defined in a set called the domain and giving one or more outputs defined in another set called the codomain. Here we have 7 maps, hence 7 functions. They all map one integer to another integer, but all differently, of course. We will write f1 of n, the value mapped to n by the first function, f2 of n, the value mapped to n by the second function, and so on. For each function, the starting value and the output value are integers, but they do not represent the same thing. 15, for instance, does not have the same meaning here if it is a seed number, a temperature, or location. That's what units are for. The first function maps integers representing seeds to integers representing soils. So, even if f1 of n could be mathematically correct, it makes no sense since the second time we apply f1, we expect a seed number, but we give it a soil number, as it is already an output from f1. As it is clear now, we do not care about the names of the maps. We could have given the name f seed to soil to the first function, but it's quite longer than f1, and we lost the semantics of it being the first function we have to apply. Here, we only care about the order of these functions. f2 of f1 of n is legal, but f1 of f2 of n is not semantically, even though, once again, it's not wrong mathematically speaking. And what we really care about is the output given by the last function when our seed number n has been transformed by all functions, finally giving a location number. That is, the value of f7 of f6 of f5 of f4 of f3 of f2 of f1 of n. Since that's a lot of parentheses, we can also write it like so, which is a notation that represents exactly the same thing, but is more readable as we understand we want the value given by the composition of all fi of an input n. Let's call these fi the intermediate functions. It is worth noticing that in math our functions are applied right to left from the closest to n to the farthest, while in our drawings the numbers are processed from left to right, as I find more intuitive to have the inputs on the left and the outputs on the right. Let's call f the composition of all our intermediate functions. The problem of the day 5 can now be written as: find the lowest value f of n for every n in the input seed set. What we'll have to do is to find a way to express f of n for a given n, and to compute f, we'll first have to know how to compute the intermediate functions. Now that we know what to do, let's write some code. In this video, we'll use Python as our programming language because it's quite easy to use and understand even if you're not familiar with it. You don't have to compile it, and it's fast enough for the kind of program we want. We're not doing rocket science here. For instance, look how easy it is to write a program displaying hello world on the screen compared to writing the same program in another language called C++. Now, don't get me wrong, I'm a huge fan of C++, but for this kind of task, we'll stick with Python. If you're already familiar with very basic Python and basic object-oriented programming, you can skip to the next chapter at 2034. If you are still here, welcome to the Python 101 zone. The first concept we'll see is what we call a variable. A variable is a way to give a symbolic name to a value. For instance, in the following Python code, we create a variable named myVariable, and through the use of the operator equal, we give it a value of 17. We can see what's inside the variable by printing it to the screen, for instance. The second concept we'll see is functions. They behave more or less like in mathematics. You give inputs, they do stuff, and you get outputs. Let's create in Python our first function to multiply a number by 2. We'll call this function doubled. Could it be even simpler? The keyword def says we create a function, we then give it a name, here doubled. Between the parentheses are the input variables, if any. Here we have only one input, represented by the variable value. Finally, the keyword return stops the function and returns something, here the input times 2. Then we can use it like so. Unlike in math, in programming, functions can have no input or no output or even neither. For instance, we have already seen the print function that takes stuff to print but technically returns nothing, just prints it on the screen, which is different. And as another example, we could think of a function returning the current time, thus taking no input. Just one more thing on functions and variables. Variables store data, but data is a rather large concept. Data can represent multiple things such as integers, real numbers, a string of characters, booleans, which are a way to express two states, true or false, and so on. In Python, we don't have to explicitly express the type of the variables we use. But when writing functions or declaring variables, we can give some hints as to what the function takes and returns, or what the variable is supposed to store. Here, we created a function named add and type hinted what the function was supposed to take and to give. Here, 2 integer inputs and 1 integer output. But in Python, nothing stops us from writing that. As long as the operation a plus b is well defined for the objects a and b, adding variables is legal. Be they integers or real numbers, that will add them as expected. In order to keep our code clean, even if that doesn't stop us from doing silly mistakes, we'll use type hinting. In this project, we will also use the concept of conditional statement. It allows the program to do something specific at a given moment, depending on if a given condition is true or false. Let's use this example. Here we have an if-else block. The condition checked here is if the variable year of birth is smaller than 1969. Depending on the results of that comparison, the instructions that are to be run are those from the if block or the else block, here printing two different messages. The comparison is done with the operator less than, which acts like a function returning true or false depending on the inputs. Using different comparison operators, we can also check for a greater value, a greater or equal value, a strictly equal value, or a strictly different value. In this video, we will also need to iterate through objects. We will create the simplest collection of objects, the list. In Python, it is written using square brackets, like so. As you can see, we can have objects with different types in the same list. Now, if we want to iterate through them, we can use the for in syntax, like so. In such a for block, we can iterate through all the objects of the list and we can manipulate the current object using a variable we declared in the block. Here, every object of the list named myList can be used once at a time through the variable element. In that example, we only print their values. If you want to know the length of a list, you can use the built-in function len. Here, our list has 4 objects. If you want to access the nth object of the list, you can use square brackets with the index of the object you want. Note that the indexing starts at 0. The first object has an index of 0, the second object an index of 1, and so on. Congratulations, that's enough basic Python for this video. In the code we'll write, we'll use a paradigm called OOP, short for Object-Oriented Programming. That is, we'll represent the data we'll manipulate as objects. An object is roughly a bunch of organized data that is used to represent concepts. The pattern that defines what the object is like is called the class, and the real objects we can manipulate are called the instances of that particular class. As an example, we could represent these shapes as instances of the class circle. Objects have fields, which are variables bounded to the instances of a class. For example, these circles have a center and the radius, as defined by the class in order to fully describe them, but the value stored per object might be different. Objects can also have methods, which are functions allowing the objects to do things. As an example, let's suppose we want to manipulate 2D shapes. We could create an object representing a circle. Let's say our circle is defined by a center point and a radius. On a plane such as a screen or a sheet of paper, a point is represented using 2 coordinates, x and y. We can create another object, point2d, that represents such concept. In Python, we would write it like that. This example is a bit verbose. The keyword class says that we are creating a new class whose name comes after. Then comes an optional description of the object in order to document our code. The init method is in Python a special method that creates the actual object, and its parameters are what we have to give to construct the said object. In Python, the first parameter of an object's method is always self, and it is a variable representing the object itself. Basically, here, what we are saying is that when we construct a 2D point, we have to give it 2 real numbers, represented by floats, x and y, and when we create a circle, we have to say where it is located by giving it a center of type point2d and radius, which is a real number. Then we create the fields of our classes, without surprise the x and y coordinates for the point, and the center and radius for the circle. Now we have 2 classes, let's create instances. Or even simpler, if we don't care that much about giving a label to the center of a circle. Now we have created a circle at position 0.6 and 23.7 with a radius of 6.5. For now, it doesn't do much. Here we just store data and we can access it through the fields we've just created. Ideally, in OOP, we shouldn't use the fields directly when dealing with an object. So, for the sake of good practice, let's create methods for a circle class to get the radius, and let's create some more to compute the diameter and the area. Note how self, the first parameter of a method, allows us to retrieve the fields we're interested in. Now, we can use these methods to manipulate an abstract representation of a circle. Now that we are familiar with Python and OOP, let's code our program. Now that the way of handling data is known, let's create real objects for our shifters and our intermediate functions. The shifters are defined by 3 numbers, as we've seen before, and the intermediate functions are defined with a list of shifters. That's a good start, but for now, these objects don't do much except storing numbers. The first thing we want to know is which shifter is to be used for a given input of an intermediate function. To apply our intermediate function to a value, we will loop through all shifters, and if we find a shifter whose start range contains our input value, we stop and return our value shifted. If we don't find any shifters matching our value, we output it back unchanged. Let's begin with our shifter objects. Let's create a function checking whether value is in the starting range of a given shifter. Let's call that function canActOn. It should take one input, one integer, the value we want to test our shifter against, and should return a boolean, true or false. To check if the shifter can act on a value, that is, the value contained in the input range of that shifter, we simply check whether the input value is greater or equal than the source range start and strictly less than the source range start plus the range length. You can convince yourself that it is strictly less than the sum and not less or equal by imagining a shifter shifting only one input. The only input that could be shifted would be the very source range start, so the condition for a value v would be written like so. A less or equal condition on the right would lead to 2 values matching the condition. And this function can be written more compactly, like we would write in maths. Now we can perform tests like this. Let's now create a method apply to our shifter objects. It takes one input, the integer value we want to shift, and returns the shifted value. The amount of the shift is simply the destination range start minus the source range start. Note that we do not check whether it is legal to apply the shift to our value. It's been done just before. Here, we only want the results of the operation. We could use it wrongly, but we won't. Now, we are done with the shifter objects. It is quite nice to notice here that for any given shifter s.dest minus s.source and s.source plus s.length would always be constant values. We will talk later about optimizing algorithms, but here we would perform extra subtraction or addition each time we want to test a value or to apply the mapping on it. Instead, we can modify the object like this. The object is constructed and used in the same way as before, but what happens inside is different. What is stored does not correspond exactly to what's been given during the construction of the objects, and if its methods do the same things as before, they do it a tiny bit better. Now, internally, the objects store the input range start, called here inmin, the input range end, or more exactly one more than the input range end, as we've seen before, called here inmax, and delta, the amount of the shift. It's not a big deal to have an extra operation, as modern computers can perform tons of computations per second, but here it makes the code more readable and we can begin to see what optimization could mean. Let's now come back to our intermediate function objects. They will have one important method, which will be about computing fi of n. We will also call this method apply, allowing us to write code like that. Let's do that. It is as simple as that. Using the for element in iterable syntax, we loop through all shifters, the variable shifter representing the shifter of the current iteration in the loop, and if we find one that can act on our value, we return the value of this transformation. If after looping through all shifters we find nothing, we simply return the same value we had as an input. It is worth mentioning that for a given input value, at most one shifter can act on it. If two or more shifters of the same intermediate function could act on the same input value, that would mean there would be two or more different outputs, and that is not possible, since for a given n and a given intermediate function fi, fi of n is well defined and has a unique value. Nothing here actually prevents two different shifters to return true on their can-act-on methods. Thus, in the current implementation of this problem, only the first shifter in the loop would trigger the shifting. So, we expect the data we use to create the objects to be consistent and to not create undefined behaviors, as we are 1. Lazy and 2. Trusting the authors of the problem to provide meaningful data. We can now test our objects, creating the seed-to-soil map from the dummy input. Everything behaves as expected. Let's now import the data from the Advent of Code text file into our data structure. We won't enter into the details of how to do that in Python, as it is not the topic of this video, but we now have two lists: seeds, a list of integers representing the seed numbers, and intermediate functions, a list containing all our intermediate functions properly constructed with the shifters. Here is a way of doing so. Not the cleanest, but it gets the job done. We now need to create our final function f, the one that takes as an input a seed number and outputs a location number. To do so, we will create a variable named value, first being our seed number input. For each intermediate function, value will be updated by the current function. And if we name our function input value, we don't even need to write the first line value equals seed number. So, for a seed input n, at first value equals n, then value equals f1 of n, then value equals f2 of f1 of n, then value equals f3 of f2 of f1 of n, and so on until value equals f of n, the composition of all our intermediate functions. Now, all we have to do is to finally solve part 1. We need for each input seed to compute its location, and then return the location with the lowest number. To do so, we'll create a variable named minLocation that, for each iteration, will keep the lowest location we've seen so far, being updated if we find a location with a lower value than the current minimal location. To begin with, we'll assign a huge value to this variable so we are sure it will be updated at least once. Let's put this value at float plus inf, which basically represents infinity, ensuring every value is lower than this one. In Python, the function min returns the minimum value of its inputs. And voila! When we run the code for the sample input, we get 35, which is the answer we expected. Let's now do the same for the real input. Yes, that's the right answer. Congrats everyone, let's now do part 2. Our character discovers that the number of seeds we tested is too low. The first line of our input actually describes ranges of seed numbers. The values come in pairs. The first number describes the start number and the second the length of the range. So, in our example, 79, 14, 55, 13 means that we'll have to test two ranges of seeds, the first one starting at 79 and having 14 seeds, so the seeds 79, 80 and so on until 92, and the second range starting at 55 and having 13 seeds, 55, 56 and so on until 67. Here, instead of 4 seed numbers, we'll have to test 14 plus 13 equals 27 seed numbers. All we have to do is to change the imports. Instead of reading the seed numbers one by one, we'll read them two by two, and instead of adding one seed number to our seed list, we'll add a range object. In Python, range of n represents the discrete interval 0n open on the right. Here, the double square brackets represent an interval of integers, not real numbers. If we want to create the closed integer interval ab in Python, we'll have to write range a b plus 1, since the discrete interval a b plus 1 open on the right is equal to the closed discrete interval ab. We can then iterate through the range iterator using the for-in syntax we've seen before. For instance, here print will be called on the value 3, 4, 5 and 6. Let's change the way we import the data. The intermediate function list doesn't change, but instead of a list named seeds, we create a list named seeds ranges containing the ranges. Here is the actual code if you're interested. So let's modify our main program. We'll iterate through our seed ranges, and for every range we've created, we'll iterate through it, calling compute location from seed on every seed of that range. We update the minimum location as we've done before. When we do that on the test input and print the minimum value, we also find 46, which is the correct answer for the dummy input. Being confident, let's find the real answer on the real dataset. Well, nothing happens. Why? Wait, it has not crashed or something. It is still running. Let's visualize where it is by adding progression bars. Ouch, it's slow. In fact, there are quite a lot of seeds to process. In the first part, there were only 20 seeds. Based on the number of seeds we can process per second, it should take more than 4 hours. That is way too long for this video. In computer science, problems have a size. For instance, if you want to find the minimum of a list, the size of the problem is the length of that list. If you want to find the shortest path allowing you to visit every city you have in mind, the size of the problem is the number of cities you think of. If you want to find the definition of a given word in a dictionary, the size of the problem is the number of words your dictionary contains. For a given problem and a given algorithm solving that problem, the size of the problem is a measure of the size of the input data. In our problem, we gave seeds to our algorithm, so the size was the number of seeds. Intuitively, we understand it's easier to find the minimum of 2 numbers versus finding the minimum of 100 numbers. It's easier to find the shortest path between 4 points versus 15. It is easier to find a word in a dictionary of 200 words versus a dictionary of hundreds of thousand words. And for us, it is easier to compute the location of 20 seed numbers versus 1 billion seed numbers. Okay, but how much easier is it? Can we quantify how easy it is for an algorithm to solve a problem? Yes, enters complexity. There are mostly 2 things we may want to measure when writing an algorithm to solve a given problem. How much time it will take before ending and hopefully give a solution, and how much space is needed, which is the memory required by the program. They are called, well, time complexity and spatial complexity, and yes, you could say you're a computer scientist performing space-time analysis and earn 2 points of charisma, even though all you want to do is 1. Know if your program will stop one day and if possible not after the end of the universe, and 2. Know if you have enough RAM or disk space to run your piece of code. Even though space complexity is truly interesting, we'll not really focus on it for this video. In fact, as opposed to time complexity, it's quite hard today to need a tremendous amount of space for simple puzzles. When computer science began to be a thing and punch cards were the only thing you had to store information, one had to be extremely careful with the spatial needs of the program. But nowadays, your algo needs 1000 gigabytes and you only have 500? Well, you buy a second hard drive and call it a day. On the other hand, as we've seen, there is a huge difference between the problem being solved in less than a second versus being solved in more than 4 hours. Time complexity isn't about measuring precisely how much time is required for the algorithm, since it does depend on a lot of factors, such as the programming language you're using, the machine you're on, how busy your computer is, and so on. In fact, when doing time complexity analysis, we focus on how many operations are needed for the algorithm to give a result, and we roughly state that all computer operations are the same, even though you may intuitively feel that it is easier to add two numbers than to divide them for a human or a computer. Time complexity analysis allows us to classify algorithms according to how their runtime evolves as the size of the input set gets higher. It's time for some examples. Let's consider a list of n integers. Let's create 3 problems whose input is our list of size n. We will create 3 functions to solve them using only the tools we've seen so far. First, let's create a function returning 1 plus the third value of our list. We assume the list has at least 3 numbers. Then, let's create a function to find the minimum of our list. Finally, let's create a function to write the multiplication table of our list, that is a times b for every a and b in our lists. To solve the first problem, we will assume we cannot use the square brackets notation we've seen before. The function would have been an easy one-liner, not really interesting for what we want to see. Let's do it differently. To solve it, we iterate through our list and keep in a dedicated variable, current index, the index of the number we are on. If our index is 3, we add 1 to the current number and return the result. Let's count the number of operations we performed. We first create a new variable, current index, then we iterate through all numbers using a for loop. For each iteration, we add 1 to the variable current index, and we check if current index is equal to 3. If it is, we add 1 to the number and return this value. So, in fact, the size of the problem doesn't matter here. What is inside the for loop will be executed exactly 3 times, our variable current index being 1, then 2, then 3, and then we return. So we have 1 operation, the creation of the variable, 2 operation adding 1 to current index and checking if it is equal to 3 that we will do 3 times, and 1 final operation adding 1 to the current number. Thus, for any list of size n, we always perform 8 operations. Let's now compute the minimum of a list. We've seen this one before. We just need to keep in mind the lowest value we've seen so far and update it when iterating through our list. Let's now count the number of operations. First, we create a variable lowest value so far, and for every element of our list, we first compute the mean between the current number and the lowest value so far, and then we update the variable with whatever the result of that computation is. As we can see, there is not a one-to-one correlation between an operation and a line of code. We have to remain attentive. After the for loop, there is no more computation to do. Lowest value so far stores what we wanted. So, since we do 1 initial operation and then 2 operations for every number from our list, in total, that's 1 plus 2 times n operations for a list of size n. And now for the multiplication table. To print the multiplication table of a list of number, we want to print on the screen a times b for every a of the list, for every b of the list. So we will nest 2 for loops. We can print several variables on the same line when using the print function by separating them with commas. The first loop will be executed once per number a in our list, so n times in total. For the same reason, the second loop will be executed n times 1 per value p, but that is n times for each number a. So we enter the body of the second for loop n squared times. Now, the body of that second loop contains 2 instructions, so that is 2 instructions for every b for every a, so in total we have 2n squared instructions for a list of size n. Okay, but what was the point of all this? Well, when we counted the number of operations, we found that for a given problem of size n, the first algorithm had a constant number of operations, the second had a plus bn operations, where a and b are 2 positive integers, and the third had a plus bn plus cn squared operations, where a, b, and c are 3 positive integers. For a modern computer, for small numbers n, it doesn't make a difference, as computers do many operations per second. But when n becomes bigger and bigger, it starts to make a difference. We start to understand that according to how the number of operations are expressed in terms of n, these 3 functions will be classified differently and have different time complexity. When we express complexity, we do not quite care about the exact number of operations. We want to express an estimation of how the total number of operations varies with respect to the problem size in order to classify the algorithm. And since no matter the complexity, the algorithm would be really fast for small values of n, we want to focus on big values of n. In fact, we can intuitively feel that if we have a constant number of operations, one more or one less doesn't make a huge difference. If you have a faster computer, a higher but still constant number of operations doesn't matter, as the numbers would still be crushed in no time. It's just like we had one unique big operation. In the second function, we have a plus bn operations, where a is 1 and b is 2. Even if b was only 1, the value of a being unrelated to n ends up being insignificant compared to the total number of operations when n goes high. What matters in that function is what happens in the for loop being responsible for the 2n operations, not the extra operation, where we declare lowest value so far and say it has a huge value. For instance, here a single square represents an operation. Let's say our algorithm has n plus a constant number of operations. No matter what the constant number of operations is, when n goes high, that constant number of operations becomes insignificant. So we could discard it from the total count for big values of n. And like we just said before, here the value of b doesn't matter, since a faster computer could crunch the numbers faster, or a better version of the algorithm would lower that value b. But that family of algorithms still depends on n, and there is a kind of proportional nature between the number of operations and n. In the third example, we have a plus bn plus cn squared operations, and we can see likewise that what matters the most is the n squared part, since a and b becomes insignificant when n goes high. Here, a square still being an operation, we can see we have n squared operations. We can add a few b times n operations, and why not a constant number a of operations unrelated to n. When n goes higher, these extra operations become insignificant compared to our n squared operations. Likewise, we could simply discard them for really big values of n. Once again, what is important is not the number c, but the link between the number of operations and n squared. Let's now introduce the big O notation. It is one of the most important tools in computer science when it comes to expressing the complexity of an algorithm. If f and j are 2 functions taking one integer as an input and outputting another integer, we say f is big O of n if there is a value n0 big enough such that for every n greater than this n0, we have f of n is less or equal than k times g of n, where k is a non-zero positive constant. It is one of the most important tools in computer science when it comes to expressing the complexity of an algorithm. The big O notation allows us to express the complexity in terms of the component that grows the faster, discarding what matters less. For instance, let's call P1, P2 and P3 the three functions expressing the exact number of operations for the problems 1, 2 and 3 depending on the length of the input list. For P1, we can find the function g such that g of n equals 1 no matter what n is. The constant n0 equals 0 and the constant k equals 8. So, for every n, we do have P1 of n is less or equal than k times g of n, and we can write P1 is big O of 1. We say big O of 1 algorithms have a constant complexity. It is important to understand that all big O of 1 algorithms don't have necessarily a constant number of operations. It only means you can find a constant number whose value is always greater or equal than the number of operations. For P2, it goes the same. Let's say g of n equals n, n0 equals 1, and k equals 3. And now we have P2 is big O of n. We say this algorithm has a linear complexity. Finally, for P3, we can say g of n equals n squared, n0 equals 3, and k equals 2.5. And we do have P3 is big O of n squared, that is a quadratic complexity. As you can see, we don't even need to find the lowest value of k, nor the very n0, where k times g of n starts to be greater than our number of operations. We only need to find numbers satisfying the condition, and we can state the complexity family of our algorithm. Here, our three problems had a polynomial complexity of degree 0, 1 and 2, but we can find problems whose complexity involve more exotic functions, such as the factorial or the logarithm, for instance. Now we understand what complexity is, let's find out how efficient our algorithm is, and what are the points we could improve. As we've said before, the size of the problem is the number of seeds. We will call this number n. Here, we will compute the complexity of the creation of the objects and the actual minimum location computation. Let's begin with the creation of the objects. We first create our intermediate function lists, as we've seen before. That is one operation. Then, for every function we read in the file, we create an empty list of shifters, one operation, and for every shifter we read in the file, we create it with the right data and add it to the list, so two operations. Once the list of shifters is done, we can create our intermediate function object and add it to the list, that is, two operations. As we can see, the number of operations here doesn't depend on the number n of seeds. It depends on two things: the number of intermediate functions our file has, and the number of shifters every function has. Of course, these numbers are known and are constant through parts 1 and 2. They don't depend on n, so they should not matter. But here, we will do the computation as if they were part of the input size, and then we'll plug in their real values, allowing us to have a complexity depending only on the number of seeds. Let's call k the number of functions our file has. The first loop will be executed k times. But what about the second loop? Remember when we said we wanted to have an upper bound for the number of operations? That's what we will do. Let's call s the maximum number of shifters a single intermediate function has per our input data. Now we can guarantee the number of iterations in the second loop is in big O of s, since it is less than or equal to s for any intermediate function. Finally, we can discard the constant number of operations that don't matter during the counting and find the data creation has a complexity of big O of k times s. Let's now count the number of operations for our main algorithm. We first create the min value variable storing the current minimum location, that is one operation. Then, for every seed number, that is, we do n times, we compute the location number of that seed number, that is, we don't know yet operations, and we update the min value. That's one operation. All we have to do is to find out the complexity of our function compute location from seeds. So, for a given value, we do. For every intermediate function, that is k times, we apply that function to our value, that is still another unknown number of times, and we update the value, one operation. After the loop, we return value, now containing a location number. So, let's find out the complexity of the function apply from our intermediate function objects. Here, for every shifter, that is at most s times, we check if the shifter can be applied to our current value, that is another unknown complexity. If it can be applied, we compute the shifting, another unknown complexity, and we end here, since the function returns the result of that computation. If after checking every shifter we couldn't find one, we simply return the same value we had as an input, so the function ends. Let's check the complexity of shifter.canActOn. We simply check two pairs of numbers, so that is a big O of 1 function. Let's check the complexity of shifter.apply, even easier, we only had two numbers, so another big O of 1 complexity. We could be lucky with our intermediate function.apply. The first shifter could be the one that actually shifts the value. But once again, we are interested in the worst case complexity, so the worst case is testing every shifter to realize not a single one matches. So, in total, this function has a complexity of big O of s. Now we know that, we can update our counting for the compute location from seeds, and we find it has a complexity of big O of k times s. Finally, we can find the complexity of the main program, we update our values, and we find out the main part has a complexity of big O of n times k times s. So, the total complexity of our algorithm is big O of k times s plus big O of n times k times s, which is big O of n times k times s, since we want the worst complexity. Since we said k and s are constants, here k is always 7 and s here is like 45 in my real input data, the complexity expressed in terms of n is linear, without much surprise. If our objects are already constructed, the time complexity is in big O of n. So, doing a basic rule of 3 to estimate how much time part 2 would have taken was the right thing to do. We double the input, we double the time needed. But here we multiply the input size by 50 million. Are there good ways to optimize an algorithm that is already linear? We cannot lie to ourselves. By the way the problem is stated, if we have n inputs, we must at least test all our input seeds to find the minimum location. Thus, the algorithm must be at least in big O of n. And when n is 1 billion, that's a lot of time. But are we doomed? What if we could change the way we measure our problem's size and thus create another algorithm? See how part 2 describes not individual number of seeds but ranges of seeds? What if we could manipulate the ranges themselves instead of the individual numbers? If we say we have r ranges and that the maximum length a range has is L, we are trying at most n equals r times L seeds. But if we can process a range as a whole, maybe the length doesn't matter and we can try only n equals r ranges. As we can see, in general, close enough inputs result in close enough outputs. That is because our intermediate functions are based on shifters, and they move a whole range altogether. So, if a and a plus 1 can be mapped by a shifter whose amount is d, they will become a plus d and a plus d plus 1 respectively. When they can't be mapped by the same shifter, their path would split, resulting in a gap between the two outputs. So, instead of computing every number of a range, we can split our initial range into new ranges, the breaking points being the points where two consecutive input numbers are mapped to two non-consecutive output numbers. These breaking points correspond to the input min and max of the shifters. After the split, we know that every range corresponds to only one shifter, so we can map each one to another output range. So, for a given intermediate function and a given range of length L, the output will be a list of, let's say, m ranges, m being hopefully significantly smaller than L. Finding the lowest value of them takes only m operations, instead of testing every number of the L values our beginning range has. For instance, here, no matter how many numbers are actually represented by the range, there will always be 4 output ranges. Okay, let's code that. Let's create a new class, the range class, with a capital R, not to be mixed up with the range generator we used in some for loops. It will represent a discrete interval open on the right. It has a min value and a max value. And that's it for now. What we want to do on the range is to split it and to shift it. Let's begin by shifting it, as it is easier. The whole range shifts by a value delta, so from min max it becomes min plus delta, max plus delta. The function returns nothing, it just modifies the object. For the splitting of a range AC, we'll first consider a simple case where we have only one breaking point, B. If we have A, B and C such that A is lower than B is lower than C, then the range AC cut in B gives the range AB and the range BC. Simple, right? We consider B to be the min value of our second range and not the max value of our first range. Remember that B is not in the discrete interval AB open on the right. If B is not between A and C, well, the range is not split. Now, let's split a range into more ranges. To do so, we will need, beside the range, a list of breaking points. We assume these points are ordered. We will keep in a list only the values of these points that are in our interval AC, surrounded by A and C, the min and max value of the range. For instance, for the range 5, 10 and the splitting point list 1, 3, 7, 8, 14, we would create the list 5, 7, 8, 10. By taking these values pairwise, we can construct the ranges corresponding to our initial range subdivided. Here, 5, 7, 7, 8 and 8, 10. Because our range structure is open on the right, it allows us to simply divide ranges and avoid making lots of off-by-one errors. Let's code the split range method of our range class. It will take a list of integers and return a list of range objects. We first create a new list containing the min value of our range, all the breaking points that are between our range min and max values, and finally, the max value of our range. Then, we create a new list for the new range objects, which will be outputted, and we do an interesting bit of code. We first compute how many valid breaking points we have, and then we use a for loop to iterate the variable index between 0 and the number of breaking points minus 1. Thus, valid point square brackets index would represent every breaking point, except the last one, because of the minus 1 in the range. And so, valid point square brackets index plus 1 would represent every breaking point except the first one. Together, they allow us to take the breaking points pairwise. We can add the newly created range object and, after the loop, return the list. Now we know how to split a range, we want to apply an intermediate function to a whole range. To do so, we need to understand where we have to split the range range accordingly, and for every new range, shift that new range according to the corresponding shifter of our intermediate function. As we saw, the breaking points can only be the min and max of our shifters. So, for a given intermediate function, we want to know all the mins and maxes of its shifters. let's create a method called computeBreakingPoint that returns an ordered list of integers corresponding to these breaking points. If the mean value of a shifter is the same as the max value of another shifter, we do not want to use this value twice. We only want to know that this value exists. So we first create a set, which is a collection of unique items. When you put an item into a set, it will be added only if the item is not already in the set. Then, for every shifter of our intermediate function, we add to the set its mean and max values. Finally, we convert this set into a list and we sort that list using Python's built-in function sort, whose complexity is in big O of n log n. We can return the list. Now we are ready to apply an intermediate function on a range. We will modify the already existing function. Instead of taking an integer, it will now take a range object and will return a list of ranges. To apply an intermediate function on a range, we first have to split it on the breaking point we've just computed. Then, for every newly split range, just like we did with integers, we iterate through all shifters to find the one we can apply. Since it is guaranteed our ranges are split by the shifters, they individually either fit in exactly one shifter or fit in none of them. So, we only have to test a shifter on a single value of the range. Since the ranges could technically be one element and that newRange.min is inside our range, we can try the shifter on that value. If the shifter can act on it, it can act on our range as a whole, and we shift the range by the shifter's delta. We exit the second for loop using Python's break instructions, as we no longer need to test the other shifters. When every range has been processed, we return the list. This is looking great, but something is bothering me. The result of computeBreakingPoint is always the same, no matter what the input range is. We shouldn't waste time computing these values every time we want to apply the function on a range. Instead, we'll store the result of that computation during the creation of the object once and for all, and use it whenever we need it. That's much better. And voila, a range can now pass through an intermediate function. In part 1, our functions turn single values into single values. Now, our intermediate functions turn a range into a list of ranges. So, there are two things to think about. How do we map the output of an intermediate function to the next intermediate function's inputs? And how many ranges will there be in our final list? Isn't that number going to be quite huge? To quickly answer the first question, we will consider our intermediate functions can take a list of ranges as inputs and output another list of ranges. That's it, for every range in our input list, we compute the output ranges and we combine them in a single list. Easy. For the second question, let's look at real data from the already solved problem. As we can see, we can indeed have simple cases and less simple cases. If a range is mapped to a list of new ranges and every output range is also mapped to a list of new ranges and so on, we have a tree of ranges, growing quite complexly. Let's try to find how many ranges we can have. Before finding the worst case scenario, let's begin with a very simple case. We only have one input range and one single shifter in our single intermediate function. Immediately, we can see that to create more output ranges, the breaking point of our intermediate function must interfere with our input. If we are fully outside, we have the same number of output ranges, here 1. If only one breakpoint splits the input, we create one more output range, here 2, and if both breaking points split the input, we create 2 more ranges in our outputs, here 3. If we now have 2 input ranges, that's the same. The more breaking points inside our input ranges, the more output ranges. As we can see, it doesn't matter where a breakpoint ends as long as it's inside a range. Here, for instance, we still have 4 ranges at the end if the 2 breaking points of our single shifter do split some ranges, be they the same or be they 2 different ranges. So, for every shifter we add in our intermediate function, we can make two breaking points split our input ranges and thus create two more ranges at most. So now, let's do some math. Let's suppose that in our initial lists we have L0 ranges. Let's suppose our intermediate functions have at most S shifters, and let's call Ln the maximum number of ranges we are dealing after they went through the intermediate functions f1, f2, and so on up to fn. Since at every step we can create only two S ranges, we have Ln plus 1 equals Ln plus 2 times S. So L1 equals L0 plus 2S, that is L0 plus 2S. L2 equals L1 plus 2S, that is L0 plus 4S. L3 equals L2 plus 2S, that is L0 plus 6S, and so on. So we can see the final number of ranges at the end is Lk equals L0 plus 2Sk. Of course, S and K are constant, as we've seen before. Here, the size of the problem would be n equals L0, so at the end we have n plus a constant number of ranges, which is great. But does that mean our algorithm is efficient? Well, that's not really the number of computations we have to perform. We only computed the number of ranges we had after the kth function. Let's compute the complexity of the code we want to write. Once again, let's divide our code into main steps. We will compute the time complexity of three main steps. First, the creation of the objects. We will call n1 its complexity. Then the main loop, where we process all our input seed ranges to get our output location ranges. We will call n2 its complexity. And finally, we will find the minimum value of these ranges and call its complexity n3. n1, n2, and n3 are three functions of n, the size of the problem, which was previously called L0, the initial number of ranges, k, the number of intermediate functions, and s, the maximum number of shifters our intermediate functions can have. Once again, k and s are constants. We will use them for the computation only. Afterward, we will plug in their real values. We won't detail every step here, as we are now familiar with complexity and know we can ignore some big O of 1 operations. To construct the objects, we iterate through our file, and for every intermediate function we read, that's k times, we read and create its shifters, that's in big O of s. Now we create the breaking point using the method computeBreakingPoint. Let's find out its complexity. We do one big O of 1 operation, then we do s times two big O of 1 operations, so that's a big O of s operations. This line is in big O of 1 too, and finally the sorting is in big O of s log s. For that operation, the size n of the problem is simply the length of that list, which is 2s at most, hence the s log s. Since s is lower than s log s, in total we have a complexity of big O of s log s for compute breaking points. Finally, our n1 is in big O of k times s times log s. Let's compute n3 first, as it is easier than n2. Let's save the best for last. Here, our ranges are all the final location ranges. Since we want to get the minimum value of them, we simply iterate through them. That is Lk times. Since we want the mean value, just like we did so far, we give in a dedicated variable the current mean. No surprises, we have a complexity n3 in big O of Lk, which is a complexity of big O of n plus sk. Let's now compute the complexity n2 when we pass our ranges through the intermediate functions. Basically, we have a list of ranges, the inputs, we let them through the first function, we have ourselves another list of ranges, and we do that for every function. That would give, for every function whose index is I, that is, we do k times, for every input range we have, that is, at most Li-1 times, we call apply on that range. It is -1 since in our notation the first function is f1 and the initial number of ranges we have is L0. Let's write the details of the function apply. First, we split the range. That's an unknown amount of operation. Then, for every new range that's an unknown number for sure, we find the right shifter to shift it. That's in big O of s as we've seen in part 1. And we shift it, a big O of 1 operation. Then, we have a list of output ranges that will be the inputs for the next iteration. Let's begin by finding the complexity of the split. The first part, where we create the valid breaking points, has a complexity of big O over x, where x is the number of breaking points of our function, that is, at most 2s. So, the complexity of the first part is in big O over s. For the second part, it's the same. What matters is the for loop where we do at most 2 - 1 iterations, each iteration being in big O of 1. In total, we also have a big O of s. Twice a big O of s is still a big O over s. So that's the complexity of the function split range. We still have ourselves in a rather complicated situation, because we can't really know for a given input range in how many ranges it will be split. What we can do instead is modify the pseudocode so that it is easier to count. Let's say we first split every input range and keep in list every split range. Now, for every range of that list of new ranges, we can shift it. And we know the number of new ranges we have is at most Li. So, even if our pseudocode is different, it still has the same complexity as before, as the operations are the same but ordered differently so we can count them. Let's compute the complexity of n2. We will sum the number of operations for every intermediate function from f1 up to fk. For every function, as we saw, that is at most Li-1 times s plus Li times s. So we have n2 is the sum of Li-1 plus Li times s for I being 1 up to k. We can get the s out of the sum and replace Li-1 and Li by their explicit formulas. Let's clean that a bit. Let's divide everything that's inside the sum to put a 2 in front of it. Now let's split our sum into two sums, one for the numbers that don't depend on I and one for the numbers that depend on I. Let's get that 2s bit out of the sum. Now on the left we sum k times a constant, here n minus s, so that is k times n minus s. On the right we multiply by a constant 2s the sum of the k first integers. The sum is a famous result we can visually see using triangles. It is equal to k times k plus 1 divided by 2, times our constant 2s, that is sk times k plus 1. We simplify the bits that cancel each other, and finally we find n2 represents at least 2 times skn plus k squared s squared operations. And since n2 grows faster than n1 and n3 for every variable, that is also the final complexity of our algorithm. Even though with the square it looks quite bad, it is actually awesome. K and s are constant numbers, they are not part of the size of the problem. So we have an algorithm for part 2 which is in big O of n. What's the difference with what we did before? Well, here our size n is not the number of seeds, but the number of ranges. From 1 billion seeds, we went to only 10 seed ranges. These numbers will be crushed in no time. Let's code what is left and solve part 2. Instead of handling every input range separately, we will combine them into a single list. So, for every intermediate function, we have a list of input ranges, and we want to compute a list of output ranges. Let's write our last function. The function will take a list of ranges, our seed ranges, and output one integer, the final minimum location. We iterate through our intermediate functions. For each one, we create an empty list to store the output ranges. For every input range, we apply the function to the range and add the new ranges to our output list. And finally, we replace our input range list with our output range list for the next iteration. After that main loop, we have our final location range list. Then we compute the minimum value and return that value. That should do it. We test the function on the dummy input, it instantly gives the right answer, 46, and if we do it on the real data, here we are. We finally have the answer. Here, we solved a problem from the advent of code. The first part of the problem was no challenge to us, as we just had to formalize and create the logic to deal with it. Part 2 could not be solved with the same algorithm, or at least not in a short amount of time, since we went from an algorithm in big O of n where n was small to an algorithm with the same complexity where n was rather huge. We then tweaked our algorithm to make it work in big O of n, where the size of the problem became not the number of seeds we had, but the number of ranges of seeds we had. And we used complexity analysis to prove our algorithm was efficient. As perfectly working, our algorithm is far from perfect. For instance, when ranges are outputted from an intermediate function, if they are close enough or even worse overlapping, they could be merged into a single one. Oh, and remember iterating through all shifters to find the one that can shift our seed or our range? That could have been improved too. It wouldn't change the overall complexity, but there is a lot we can do to improve our algorithm. The Python I use is not that Pythonic, and I hope I didn't upset my fellow Pythonese by using a rather inefficient syntax. What I tried to do here is not to show you how to craft the most efficient and maybe unreadable algorithm, but to understand what are the problems we face and the tools we used in computer science. I used a puzzle from a lovely challenge to illustrate this. There were, of course, many other ways to tackle this problem. Mathematically, there is also a lot of approximations, like the way we dealt with the big O notation as if it was a number, in order not to make the video more complicated, or the way we talked about the big O notation and not the big theta notation. That would sometimes make more sense. I hope my fellow maths enjoyers and computer scientists will forgive me on this one, as I intended not to give a course on computer science, but to show a bit of what computer science or complexity is about in a fun way. I hope you enjoyed this video as much as I enjoyed making it, and I'd like to thank the people who helped me during this project. Maël, Evan, Elsa, Baptiste, Antoine, Bertie and Rouen, thank you. I hope if these topics were new to you, you found interest in them and learned something, and if you were already familiar with basic computer science, you were pleased with the way it was shown. Let me know in the comments. I will read every feedback, so if I ever make another video, I will know what to improve. Cheers!